Congratulations to the guys from Ryder, and I've forgotten your name, but well done. That's a very difficult thing to do live. Our next speaker is from Stenson Varming. For those of you who don't know, Stenson Varming is a large organisation in Australia, and Chris has come all the way from Sydney this morning to speak to us. Chris is a mechanical engineer by training, and he's got a keen interest in sustainable design. He's here this morning to share with us an examination into BIM feasibility and looking at the working with existing infrastructure. Ladies and gentlemen, Mr. Chris Locke. I guess given that we're on YouTube, we have to keep making some sound in case anybody's watching. We're now lining up an Apple to work with the presentation, which is always good to see. I'm an Apple fan myself. Okay, it's over to Chris. Thank you very much.
Excellent. It looks like we're all up and running. Thank you for the introduction. My name is Chris Locke, so I'm currently the BIM manager at Stenson Varming. Stenson Varming is originally a Danish engineering firm that was established in Copenhagen in the early 1930s and moved to Sydney after winning the design contract for the HVAC on the Sydney Opera House. So last year we we're fortunate enough to able to celebrate our 40th anniversary with the Opera House, which was a fantastic point in our company's time. The design of the Sydney Opera House was quite interesting, and when I was putting together this presentation, I thought I would use that as an analogy of a lot of the work that we do here, currently today. Like most projects of the time, the original design was actually done by pen and paper. A lot of sections, a lot of elevations were put together to try and articulate the challenges of such a complex structure. But it wasn't too far down the track that they realised really something else was needed, and at a great cost at the time, they decided to commission a three-dimensional model to be put together to try and communicate not only to the public what this structure was going to look like, but also to the constructors, how this thing was actually going to be put together. What was unique about the way that this was done was because of the unique sort of construction of the Opera House, they decided to put this model together with perspex so you could see through the model itself. And not only did the model actually show the structure, how the actual foundations were going to be put together, but it also detailed the HVAC design as well. I'll see if I can get this laser pointer working. So if you sort of look there right at the back of the model itself, you can see that they've actually taken the care to model the ductwork, the main reticulation pipework in the model. So the model itself took 5 years to build. By a gentleman named Bill Lambert down the bottom there. And it was actually put into storage for many years and recently has been found and put on exhibition in Customs House in Circular Quay. If anyone's in Sydney, well worth a look. The interesting thing about this was the fact that even back then, back in the 1950s when they were establishing ideas about how this was going to be put together, there was still a need for a visual 3D interface. People needed to understand how this complex structure was going to be put together, not only from a constructible point of view, but also from an interface point of view. How are we going to work with another company? So a lot of the work that we still do today is existing infrastructure. In fact, it probably makes up more than 50% of the work that we do. Some of them are very large projects. We're at the tail end of a hospital currently, and some of them are quite small, bespoke projects. One that I've chosen to talk about this morning is a suburban shopping mall, which is 10 kilometres out of Sydney CBD. The architect, the landscape architect that came up with the original design, developed the solutions there by hand. It was a very aggressive time frame, and the architect had decided at that point to continue documenting by hand, which is quite unique in today's day and age. But as you can see down there on the bottom corner there, these were the drawings that we received in order to do our portion of the work. So we were commissioned to do lighting design and power reticulation. There was also a survey done. Now, the survey was completed in traditional 2D, but it had three-dimensional values inserted in the CAD file, and that was all we had. 3 years ago, Stenson Varming as a company drew a line in the sand and committed to doing every project in BIM. So when we got this one over the table, it was quite unique in that way because there was no one else in the design team that was operating in this space. So what we were able to do was we extracted the values from AutoCAD, imported them into Revit, and developed a topography from that, and were able to then start modelling the elements that we were interested in. I have been approached and asked the question, well, what benefit did that provide to you? What benefit did that give the client? Lighting design is a very complex and, I guess, visual type of pursuit. And being able to communicate how light falls into structures, how light is manipulated and changes as it passes through foliage and trees and the like, can be discussed, but is better shown visually, and we were able to do this quite successfully in this project. But another one of those nice little outputs that we got from it was that there was actually quite a significant grade across the project, and we were able to quite accurately calculate our voltage drops and our quantity-based elements, the number of pits that we needed, the number of light fittings, how long the conduits were from this. And when we presented it back to the council, they were extremely happy with what we had been able to achieve. So the problem is with existing infrastructure is that there really isn't any direction. And there's a lot of opinions about how it's done, but often there's this, I guess, unwillingness to proceed into areas of a structure that is not necessarily part of the contract. So there's a very distinct interface, and most of the time these interfaces are incredibly important to the new part of what you're trying to put together. So how do you actually get this to work? How do you actually get this to put together? More often than not, CAD files are actually provided to us, and a lot of the time that's a really great starting point. But when you get to that point where you realise that something doesn't line up, or perhaps something has changed over the years, and you've got to start carrying out site inspections, that's when the whole process becomes a little bit antiquated, a little bit time-consuming. I'll put up here a little question: what do clients want? Now, in this particular instance, when I'm talking about interfacing into existing structure, there are two main types of clients that we work with. There are constructors, and what do they want? Well, they want to be able to mitigate risk. They want to be able to be assured that the designs that we're putting forward work, that they can pull ceilings down, and what we've documented will actually interface with what they find there. And then there's the other type of client, which are the end users. So we do a lot of work with clients like government facilities, health infrastructure, universities, that are also obviously interested in construction programs and when the facility is going to be up and running. But also, they're very interested in how they can use these elements to update their asset management records, to update their FM systems. So how do we actually interface BIM into existing infrastructure-based projects? The key here really is accuracy of information. So if you have a high level of assurity that the information that you have is correct, then you certainly can proceed with CAD-based elements. The way we manage this is we actually develop a separate model altogether. We import the CAD files into that, and we do remodel elements based off the CAD files or based off the hand drawings, able to be assured that the systems that we're putting in will actually work. So when we actually approach these things, we tend to find that, particularly with large organisations, there are, even with organisations that haven't yet engaged in BIM, there are often a number of systems out there that we look to try and interface to. So one of the key things that we look to do is to understand how currently assets and facilities are being tracked and managed. More than often or not, that is in some form of database. And whilst my esteemed colleagues that presented previously have talked about standardised systems across the industry, which absolutely is the long-term goal, more often than not, we actually find that institutions and organisations have their own systems. So we tend to look to customising that output. So one of the solutions that we've come to, and Sam Collard just briefly talked about this, but I'll go into a little bit more detail. Laser scanning is a process of rapid data capture. So what do I mean by that? Well, a laser scanner, I'm sure most of you have heard people talk about a laser scanner, but today's laser scanner is that size there. So it weighs about 5 kilograms. They're very nondescript. When you talk about a laser scanner, people have visions of lasers shooting around everywhere. They actually operate off the non-visible light spectrum. This picture here was taken of us laser scanning in the Great Hall at Sydney University. Each scan that we generate takes about 15 minutes. The accuracy of those scans are very, very high. So the current standard out-of-the-box scanner that we're using, which is a Faraday-based unit, scans into an accuracy of plus or minus 2 millimetres at 25 metres. Now, what does it actually do? Well, in functional description, I guess, it fires out a laser. When it hits a solid object, it records the X, Y, and Z value. And it does that very, very quickly at a very rapid rate. So the units today will do that at about 50,000 times a second. Once it's finished doing that, most of the scanners that we use today anyway will go through a photographic session. So it will then take photos of everything that it sees as well, and then we'll overlay the points and the photos together to provide a colorised point at each location. Now, please be aware that this isn't, the intent of this isn't for a photo, the intent isn't for a realistic image, the intent is for the information that's contained within it. So often I'll show these to people and they sort of think, well, I can get a better image if I just take a photo, but it's not about the image, it's about the information. So there are a few little mishaps there, and if someone happens to walk by while a photo's been taken, it will lay that person into the points behind it. But generally speaking, when you think about the information that you're capturing, that's what this is all about. The cost, so particularly in Australia, laser scanning came to Australia at least 10 years ago, perhaps even longer, primarily used in the mining sector. And being in that sector, they were able to ask for extraordinary prices, and the miners were happy to pay for it. But the cost has come down hugely in the last 5 years. We operate now with these whenever we have an existing project with existing infrastructure rather, and we're looking to capture more information. This is just our standard workflow now. There isn't any further question. If we're comparing sending someone out to site to start site measuring, then you're just going to lose huge sums of money compared to this process. Now, it's not really about the things that you go out to site to find. I mean, that's a given. It's about the things that you don't know about yet. Okay, so you go out to site, you measure out a chiller, you measure out a cable tray, whatever it is that you're looking at, you get back to the office, and then you sort of think, I wonder where that penetration was. I wonder where the cooling tower sat, The point cloud scans will capture all that. It will capture everything there. So it gives you all that information, and that's the real key. So, I will quantify at this point that the laser scanners are not X-ray machines. They don't go through solid objects. If I was interested in scanning the ductwork above the ceiling in this room, I would have to get the scanner either above the ceiling or I'd have to drop the ceiling altogether. So it won't scan through solid elements, it will just scan what it sees. And that also means that if I have a complex shape, a complex space, like a dense plant room, I'm going to have to take a whole range of scans in order to capture all the information inside that space. So it is a line of sight device, and that's probably the easiest way to think about it. A few points there. Some of the older scanners can be dangerous to eyesight, so there's something that you just have to be aware of, although the units that we use today are all eye safe. Once the scanning has been complete, you then have to associate the scans together. So again, if we were to scan this room in here, we may take 4 scans. There will then be what they call a registration process, where we associate one scan location to the next. Now, the accuracy of each specific scan is very high. There can be some tolerance when you register one scan to another, and that should be considered. So the end game here really is to establish what it is that you're trying to seek out, what it is that you're trying to establish at the end. This isn't a traditional survey as such, it's about capturing information. Generally speaking, the time when we started this, the time that we would spend scanning on site and the time that we would spend registering or associating scans in the office was about 1-to-1, but we have found that the software are going, advancing in leaps and bounds at the moment, and that's probably reduced somewhat, probably by about 25%. So how long does a laser scan take? Well, that's really difficult to answer. It just really depends on the shape of the room and the amount of information that you're trying to capture. It's really easy to get carried away with the point cloud scanning, and I'll finish the presentation soon by showing you an actual output. It has huge amounts of information in there. I mean, it is absolutely colossal, the amount of data that is able to be captured now. But please remember, a point cloud scan is not a BIM. That's not where the journey ends, it's where the journey begins. So once you have this point cloud scan, then what do you do at that point? Now, with existing infrastructure, a lot of the time it's really about being aware of whether something is going to work, whether something is going to fit. Now, we can use Navisworks to clash against a PCS. And that's a really good starting point, is cleaning up a point cloud scan and then being able to clash your BIM against a point cloud scan itself. The point cloud scans have huge amounts of information in them. So the LOD that we heard discussed before, the level of detail, is very, very high. When we convert into BIM, there has to be a fairly mature discussion about how much time you want to invest in putting that level of detail back into it. Generally speaking, in the space that we operated in as design consultants, that sits somewhere around 300. So, establishing control. This is something really important. The output of the point cloud scan, what we're going to use this for, I briefly mentioned before, is critical to understanding how you actually put this scan together. So if the exact dimensions of this entire space was critical, you would still need to survey particular locations to tie those scans into those locations. However, most of the time for what we do, that's not really needed. What you see there is actually a placed target inside the scan, which is a sphere that we use to associate one to another, but we're actually finding now with the latest software that these aren't really even needed in most instances where the software is able to pick up geometry. Once we actually get it into BIM, there's 2 ways we can deal with this. We can either use the point cloud scan as essentially as a veil, or a framework in which to build up a BIM from. So we can just operate that manually if we wish. But what we have been playing with now for about the last 6 months is point cloud extraction, where we actually go into a BIM and we start to associate density of points with physical objects. So we operate off a Revit platform. We can open up Revit and sort of tell Revit that face is a wall, that surface is a floor, We have now moved into HVAC elements, so it will start to understand pipes, it will start to understand ducts. This isn't a magic convert to BIM button, so please be aware of that. It's still an element by element process, but certainly it is a highly accurate process, but it still takes time. One of the projects I'll talk about at the end, which was of a services tunnel in a hospital, had a pipe, a drainage pipe that was about 300 metres long. When we carried out the scan, Rivet was wanting to put bends all the way through it, and the reason why is because over that length the pipe had actually drooped, just by a few millimetres, but it had drooped enough that Rivet and the PCS conversion software had picked it up and it was telling us, hey, there's something wrong here. So once we have information into BIM, you know, what do we do with it? Well, obviously there's the obvious side. You know, we need to generate drawings, we need to generate design, but we've actually taken that one step further now, and we start to use the BIM for design. So one of the areas, particularly that we're focusing here in Hong Kong with, is lighting design, and we exclusively now use our BIMs to carry out lighting analysis. I can't recall, one of the previous presentations talked about using Dialux. We use an add-in package called Elim Tools, similar sort of approach, but it works within the Rivet model. And the previous process to that, how we were operating beforehand, was that we would get a model into the office to carry out design with, and our lighting designers sitting aside us would then spend huge amounts of time building a three-dimensional model up in their own AGI software to carry out the very same analysis. So we're starting to find these quite obvious efficiency gains in establishing this information when we have the data available to us. There has also been a shift, particularly in Australia. I assume this is not singly in Australia, that we are starting to get very early contractor engagement, where clients are starting to get builders in very early to give them advice about cost, to give them advice about constructability. And just recently we've completed a university project in Sydney, and this particular workflow occurred in that very way. And one of the things they wanted to do is they wanted to come back with alternate solutions. So they sort of had a look at the way the plant room was designed, the way a plant room was put together, and said, well, look, that's fine, but we can save X amount of dollars if we do this. Now, obviously, as a design consultant, you may look at that and think, well, that's fine, but does it work? I mean, give us a level of confidence that this option will actually operate in that fashion. And again, once you're in this space, it's a simple process. It really is, of validating whether something's physically going to operate, whether something's functionally going to work, establishing what the pressure drop is on an exhaust run. Essentially, it provides transparency not only to us, but it forces transparency to everyone in the design process. So, look, just to go over the obvious points, once you're in BIM, that sort of tedious administrative task of managing hundreds and hundreds of drawings disappears. I've got a single model sitting there. If I want to update the drawing name, I do it once and it gets done everywhere for me. The data that we use between HVAC designers, electrical engineers, lighting designers, hydraulics guys is all the same. We're all using the same area. We're all using the same numbers. There are no shifts in the way people calculate things. The generation of equipment schedules all happens automatically, and then we are talking with particularly a number of builders at the moment about design for manufacture elements as well. So look, I've got a number of case studies here. The first one, I'll sort of fall back to the Sydney Opera House again. Part of our present to the Sydney Opera House on its 40th anniversary was to deliver a BIM model to them. And when I sat down with our Managing Director, Dan McKenzie, we sort of came up with deciding to put together a BIM model of one of the plant rooms, which sat in the deep bowels of the Sydney Opera House, plant room number 8. We spent about 4 hours laser scanning this in. and then another 36 converting this. So what you see here is 40 hours of work from the beginning to the end. We populated the data, populated the BIM elements with COBie data, and then we also associated the existing FM system into that database as well. It was quite interesting because at the end of the project, Dan sat me down and said, okay, how much time have we spent on this? And I said, 40 hours. And he sort of, are you sure it was only 40 hours? And that's honestly the entire time it took to actually generate that. And you can see, like, we haven't gone to huge amounts of detail, but we've gone to enough detail to locate every element, identify every piece of kit in that space. The second project was Westmead Hospital. So it's one of the largest hospitals in Sydney. It's currently undergoing a $4 billion refurbishment. It was a very, very aggressive procurement time when it was initially built in the 1970s. The architects hadn't finished designing the place when the government at the time wanted it to be constructed, so they dug these tunnels underneath the lower ground slab in order to actually reticulate all the information. So it was very much done on the fly. They put huge amounts of, as you can imagine, there are huge amounts of services underneath the hospital. None of it was actually documented. So when this new refurbishment came up, they gave us a call and sort of asked us what we could do for them. And we went in there and laser scanned and converted the tunnels for them into BIM. So what you see there on the top left is the central energy plant there, and that's just an image of the services tunnels, which ran for about 1 kilometre. Needless to say, I will sort of mention at this point that the auto registration didn't work on this particular one. There were just too many pipes that all looked like pipes, and the software did need to have its handheld to associate one scan to the next. And the last thing I want to say today is it was actually a fairly small project. Sydney Harbour has 3 major bridges in it. Obviously, the Sydney Harbour Bridge, there's the Anzac Bridge, which is relatively new, and a bridge that not many people know about called the Gladesville Bridge was built in the 1950s, had its 50th anniversary September this year, and it's the 3rd biggest bridge in Sydney. It's a concrete structure, and it's whenever we talk to the Department of Main Roads, they sort of quietly chuckle to themselves because the entire cost of construction of the Gladesville Bridge was less than what it takes to maintain the Harbour Bridge on an annual basis, being a steel structure. In any case, we went to the Department of Main Roads and asked them for the drawings. They didn't have any. They'd lost them over the years. So they sort of said, look, what we want to do is we want to light the substructure, but we can't really give you any information about how to do that. Very, very quick turnaround, very low fee. So what we decided to do was to go in and laser scan it. So what I'll do is I'll give you a live demo of exactly what we were able to achieve here. Okay, so this scan here we put together in a day and a half. Again, the intent of the scan was to gain information about the physical elements, was to convert this into a BIM so we could carry out some lighting analysis before spending time out on site actually putting this stuff together. So this is some Autodesk software we're using here that demonstrates the scan. It was done relatively low resolution because what we were interested in was the structural components of that. This wasn't a survey. Okay. So one of the concerns that we had that we were firing LED lights in, there were buildings built very, very close to the sides of the of the bridge, and we were using LED lights because of their directional capabilities. But as you can see, the closeness of these were very, 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 very prevalent. We did actually carry out a range of scans on top of the bridge too. Often when I show this, particularly to some of the older engineers in the office, they sort of look at me and say, but how did you get up so high in order to carry out the scans down below? And I try to explain to them it's just a matter of capturing points, and it doesn't matter then where you locate yourself in the project. But you can see there, this marina was about 300 metres away, and this is a standard off-the-shelf ferry unit. It took us about half a day to put this BIM together. What we captured was the main structure, the columns, and the roadway overhead. And the advantages that we had, obviously, was that we were able to turn up to site. We put the lights in, the intensities and the locations were perfect. It really just came down to a conversation of colour. That was more or less it. So we did the setup within in one evening, and the department was very, very happy. But that concludes my my talk today. Certainly, if you have any questions, I'll be around the rest of the day. Feel free to give me a yell. Thank you very much.